Okay, so here's what is first, the squeeze theorem. What I'm going to do is I'm going to just let you write this down, and then we can talk about what it means. Okay? Okay, so the squeeze theorem is what it sounds like, okay? Basically, if you have two functions, in this case h and g, and they, as x approaches c, they both have the same limit, L. If there is a function, in this case f, that is in between, so it's being squeezed in between the other two, all right, then the limit as x approaches c would also be that limit, L. So you see how f is in between those two functions always. Your two, like, pieces of bread, right, for the sandwich, they have the same limit at c. So what's in between them must also have that same limit, just at that c value. Everywhere else it's obviously different, okay? But at that c value, it would have the same one. So let's kind of see what this looks like, okay? We want to find the limit of f of x. Let's see, x sine of 1 over x as x approaches 0, okay? So first of all, can we use direct substitution and just like plug in 0? No. All right, let's get our calculators out. Let's graph this to see what it looks like. So it's x sine of 1 over x. Let's also be clear that when you are graphing anything in with trigonometry, make sure that your mode is in radian mode. Okay? Okay, so it gets really funky. Like I've zoomed in pretty far. Okay, so it's basically like a 1 by 1 right now. All right. So we got some crazy things happening. Some of you graphically can probably figure out what maybe the limit's going to be. Okay, but we don't really know right now. So what we need to do, let's think of two functions we could squeeze that function in between. Okay. We know that the sign of anything, well, in this case, the sign has to be between which two numbers? Like the sign has outputs that are in between what two ranges? -1 and 1. Okay? So the sign of 1 over x is not going to give us outputs bigger than 1 or less than 1. Okay? So if we think about this x right here, would you agree that y equals the absolute value of x would always be bigger than f of x if sign is only giving us outputs between -1 and 1? Okay. Do you agree that y equals negative absolute value of x would always be smaller than f of x? Okay, so let's go ahead and graph those two together. This is much cooler when you have like that calculator with the colors, right? So you can see the difference. Before our computers got updated to Windows 10, I had that up here to use, but it doesn't work with the Windows 10. Yes.
Where is absolute value?
It's under math, and then if you arrow over to number. Okay. Is f of x squeezed in between those two absolute values? Okay. So this is what we know. Come on. There we go. This is what we know. We know the limits as x approaches 0 of the absolute value of x would be 0. We know the limits as x approaches 0 of negative absolute value of x would also be 0. Since f of x is squeezed in between those two, so let me get this down. No. Okay. Since we know that it's squeezed in between, then the limit as x approaches 0 of x sine of 1 over x would also be 0. Okay. I'm going to be honest with you, the squeeze theorem does not pop up very often, okay? But it's something that you need to be aware of, be able to understand. You may see a problem here or there, but it's going to be one of your least popular techniques for limits, okay? All right, let's switch gears a little bit here. Trigonometry, okay? We can use direct substitution to evaluate trigonometric functions or trigonometric limits. Okay? Okay? Here is one time out of many where your knowledge of the unit circle will come in handy. Okay, so as long as we are able to plug in the C value with direct substitution, we don't get any divide by 0, we can use direct substitution. So the limit as x approaches pi over 3 of secant of x, all we have to do is plug in pi over 3 to the secant, and the secant of the pi over 3 is what, April? 2. Since the cosine is 1/2, the secant is 2. Okay. Same thing here. The limit as x approaches pi over 6 of tangent of x. All we have to do is evaluate the tangent of 5 pi over 6. And the tangent of 5 pi over 6 would be what, Will?
Radical theorem of 3. Or negative radical theorem.
Which one?
Negative.
Okay. Good. All right, can you handle those? Remember, if you have to draw out like the first quadrant to get a couple coordinates, okay, do what you got to do, but you do need to be able to think of these quickly so you can save your time for the ones that need some algebra. Okay, we have 2 special rules that involve trigonometric limits. I'm going to have you write them down, and then we're going to practice using them. Go ahead and get this picture here. Here are our 2 special trigonometric limits. A lot of syllables in this. Okay. Now, as you're writing these down, okay, maybe you have noticed, maybe you have not, but by using direct substitution with both of these, you get 0 over 0. Okay. Now, there are proofs for these 2 limits. I am not going to go through these at this time. If you would like to look at them in your book, you are welcome to. But for right now, let's just accept the fact that these are 2 rules that we need to know. Okay? When we learn something called L'Hopital's rule, we'll come back to these, and it'll be one way for us to verify that these are correct. But for right now, I need you to just accept that these are true. Okay? We will do some proofs throughout the year, but these aren't ones that I want to spend time on today. So I want to go ahead and talk about this right here. The limit as x approaches 0 of sine of 2x over 2x. All right. Our rule, okay, just has an x. And here we have a 2x and then a 2x in the denominator. This is still going to be 1. What I need you to understand is as long as the angle matches the denominator, then this rule can be applied. So it can be a star, it can be 15x, it can be y. It doesn't matter. As long as the angle matches the denominator, you're going to be okay. Also, we can talk about the reciprocal being true. Okay? since we're talking about 1, right, if we take the reciprocal, well, the reciprocal of 1 is 1, okay? So it's going to work both ways for that sign limit. All right, so I think I have 3 examples that we're going to go through together. All right? Any questions before we get to there? Okay. Go ahead and write. Let me get. I don't know why these screen sheets. Let's talk about this one. Okay. Now, in calculus, you are going to have to be creative at times. Okay. In pre-calculus, you went through a long, well, maybe not long, but a pretty decent chapter all about trig identities. Okay? Here is the time you get to use them throughout calculus to make your life easier. Okay? Now, if we try to use direct substitution, tangent of 0 divided by 0, not okay, is it? Okay? If only there was something that we could do to rewrite this. Suggestions?
I believe it's the trig identities for the tangent are sine of x plus 1 and 1 minus cosine. So you can,
Say that again?
it's sine of x plus 1 is 1 and 1 minus cosine of x. Maybe it's C.
Okay, I think you're thinking of, okay, sine squared plus cosine squared equals 1. And there's one with tangent squared and secant squared. So those Pythagorean ones, are those the ones you're thinking of?
Yeah, that was a long time.
That was a long time ago. Okay, since that is just tangent, we can't use the Pythagorean ones because it would need to be tangent squared instead. Okay? But I like that you were brave and raised your hand and we gave it a try. All right, let's keep thinking though. Eric, did you have your hand up?
Isn't it sine over cosine?
That is an identity. That is equivalent. Oh no, what did I do? I broke my rule. Okay. Make sure you write the limit until you evaluate it. Okay, so sine over cosine of x all over x. Do you think that could be helpful? We have a sine x and we have an x, right? Maybe we can somehow group those together. Okay, so let's recall that when we divide, it's the same thing as multiplying by the reciprocal, right? So we have our numerator times the reciprocal of our denominator. So what I would do is, since we have that special rule, I would group sine of x and x together, and then 1 and cosine of x together. Like, that's okay. That's the commutative property. We can put things in a different order. All right? Now, we know the limit as x approaches 0 of sine of x over x is what? Is 1. So I'm going to do this. I know that this goes to 1. That's kind of my little notation for, okay, I know what that limit is. All right? And so now what we can do, that limit goes to 1, and now we can plug in 0 to what we have left over. And what's the cosine of 0? 1. So if you can use identities, whether algebraic or trigonometric, to group sine of x over x together, okay, we can make that special limit work. It just has to be going towards 0, otherwise it's not going to work. All right, go ahead and write this next one down. Okay. So first of all, we think direct substitution. When we plug in 0, we get the sine of 0 over 0. Okay? That's not good. Does this look kind of familiar? I mean, it looks similar to that special rule, right? What would need to be true in order for us to be able to use the special rule? We would need to have a 5u in order for that to be able to work. Okay, so let's use some algebra skills here. What could we do in order to force that denominator to be a 5u?
Can you multiply 5 to go to the top and bottom?
Okay, we can multiply by 5 over 5. It's like multiplying by 1. It's not changing the value of our expression. Okay, so we have the limit as u approaches 0 of 5 times the sine of 5u over 5u. Okay, so now these group together, all right, as that goes towards 0, that limit will be 1. That's our special rule. So what we have is 5 times 1. Okay. All right. You ready to step it up enough? I have faith in you. Think we can get through this last example. We use direct substitution. We get the sine of 0 over the sine of 0, which is 0 over 0. Okay? We can't do that, which means we need to rely on some technique to help us. Okay? Does anybody have any thoughts, suggestions, ideas? Kelly?
We could somehow try to get them both to 15 theta. Because it's like common multiple.
Okay. Okay. The trouble with that is we would have to use some major trig identities that we probably are not very comfortable with off the top of our head. Okay? I like where you're thinking though. Okay? Yeah.
We could break it for like 1 over sine of 5 theta times sine of 3 theta over 1.
Okay, so kind of write it as 2 separate fractions. I'm using blue and it's writing red. It's uncomfortable for me. Okay. So kind of like this?
Yeah.
Okay, I like that. Kind of 2 different thoughts here. All right. We think to our special limits, what would we want on the other side of those fraction brackets?
If you multiply the first fraction by 3 over 3 and the second one by 5 over 5.
So like, hold on, let me make sure. Like this. Would that be sufficient to?
Something like 3 theta.
Okay. So if we multiply by 3 theta over 3 theta and 5 theta over 5 theta, like that? What do you think of that suggestion? Give it a try? Okay. Let's talk about why we suggested that. Okay, if we have 3 theta times sine of 3 theta over 3 theta, okay, we can apply our special rule there. Same thing here, 5 theta over 5 theta times sine of 5 theta. Okay, we can apply our special rule here. Okay, so sine of 3 theta over 3 theta, as theta goes to, how about, let's try 0 there. As theta goes to 0, that one's going to go to 1. 5 theta over sine of 5 theta, that is also going to go to 1. So what we're left with is the limit as theta approaches 0. We have 3 theta left over times 1 over 5 theta left over times 1. What? It is still 0 over the 0, but what can we do algebraically there to help us out? Can we cancel those out? Okay. So we're left with the limit as theta approaches 0 of 3/5, and we know that the limit towards, it doesn't matter, of a constant is going to be that constant. Good. All right, so your homework, is going to be on your gold sheet. So I would look at your gold